Okay, so limiting reactants is not a difficult concept to get, although I have a lot of students who tend to have trouble recognizing limiting reactant problems. And so if you've not watched the video, that's okay because we're going to kind of discuss it for just a few minutes and then we're going to work a problem. But I am going to suggest that if you've not watched the video, go watch the video so that that way you can get a little bit of extra reinforcement. If you have watched the video after we finish, you may want to go back and just, run through it. But anyway, so we're going to talk a little bit about limiting reactants today. So I've got two definitions here. A limiting reactant is basically what its name is. It is a reactant that's going to limit the amount of products that you make, meaning that you're going to run out of the limiting reactant before you produce the maximum number of products that you could actually make. So it limits us in how much we can produce. Now, throughout this unit, we've seen in excess of, or in excess of this, or oxygen in excess, or chlorine in excess. And a couple of times I told you just don't worry about that because you don't need to. Well, now we're going to talk about what that means. Anytime you see excess or in excess, they are pointing out what the excess reactant means, meaning that you will never run out of that. If you need 9 bajillion moles of oxygen, then there are 9 bajillion moles available to you. So an excess reactant means you have plenty of it. And so therefore you can make the maximum product that you're going to need, okay, or that you want to make. So in the video, I use an example of bicycles, frames and bicycle tires, and we talk about how many bikes you can make. And if you've not watched the video, you may want to go back and watch that so you'll know what I'm talking about. But I'm going to use another real life example. This is one that happens quite often in my house. It never fails when I get ready to cook something. I'm not going to have enough of something, it seems like. I have to be very particular about how much of something I'm going to make, or how much of something I'm going to make, and if I have enough ingredients to do that. And one thing that I have to make every now and then for, church or Girl Scouts with that are brownies. So I have this scenario here for you. I have to make brownies, and I have bought 12 brownie mixes, and they're in my cabinet, and it's ready for me to make brownies. So I pull out all 12 of my brownie mixes. I have them on the counter. I'm prepared to start whipping them up, and each one of those mixes calls for 2 eggs and 1 cup of milk. So I have 12 brownie mixes. Each brownie mix needs 2 eggs and it needs 1 cup of milk. Okay. So I go to my refrigerator and I pull out my ingredients, and I have 12 eggs and I have 12 cups of milk exactly. So take a second, look at this, and tell me, how many brownie mixes can I make? And if you've got it, unmute and tell me.
6.
Okay, I can make 6 brownie mixes. Now, Jolie says I can make 6 brownie mixes, and that's because I only have 12 eggs. In my household, what would have happened is Mr. Fortenberry and Jackson, for a midnight snack, would have scrambled up 2 dozen eggs and then played Xbox into the night. And therefore, I have run out of eggs. I don't have enough eggs. I'm down to 12. How many eggs do I need in order to fix all 12 of these brownie mixes?
Another dozen.
I need another dozen. I need 12 more. In order to make all 12 brownie mixes, I need 24 eggs, but I'm down to 12. I have plenty of milk, but I've run out of eggs, okay? So now let's use our new vocabulary terms, okay? Looking at that brownie mix, which one of these ingredients is my limiting reactant?
The eggs.
The eggs. I am running out of eggs. I don't have enough eggs. So therefore, that is my limiting reactant. It is limiting me to only 6 brownie mixes. I do, however, have 12 cups of milk. Those 12 cups of milk allow me to make all 12 brownie mix. Therefore, they are what we know as my excess reactant. It is allowing me to fix the maximum number of brownie mixes. Claire Beth McCullough, every time you have another dog with you. Is it like a dog farm?
I own a petting zoo,
I'm
basically.
beginning to wonder every time I turn around, there's another dog.
I
Okay.
have 4.
Wow. I only have 2, and I thought that was excess. Well, so there we go. This is how we would use those 2 chemical terms or chemistry terms in a normal everyday thing. And I'm sure that everybody in this room at some point has gotten ready to make something and you realize, oh, shoot, I can't make as much as I thought I could, or I don't have enough of this to get all that I want to. And then what I would do is I would have to run back to the store to pick up another 12 eggs, another dozen eggs, in order to fix all of my brownie mixes. And more than likely, just to be careful, instead of picking up 1 dozen, I would pick up 2 dozen, which means that then I have an excess of eggs, okay? So we're gonna apply the same concept that you use every day into actual chemical reactions, okay? So I've got a few little things that I want you to know whenever we're doing these problems. It's just some rules that I like to use. So here are 5 steps in working limiting reactants, okay? So 5 steps to work LR problems, okay? So the very first thing that you need to do is you need to ID the knowns. In a limiting reactant problem, there is more than likely there will be more than 1 known. The problems we've been working so far only have 1 known, but now you're going to have 2, okay? So you're going to identify the knowns and you're going to write those down, okay? So after you've identified the knowns, if the 2 knowns are both on the reactant side, it is a LR, limiting reactant problem. Probably the number 1 complaint that my students have had over the years when doing stoichiometry, once they get the hang of it and they understand how to set up a stoichiometry problem, stoichiometry is pretty easy. I enjoy doing stoichiometry because I like things that fit, and to me, it's like a puzzle. And so my students, once they get over that hump and they realize how to work a stoichiometry problem, then the next difficult thing for them is when we do LRs and they're like, Miss Fortenberry, I don't know when I'm going to use this particular problem type. So if this was an actual problem, let's just say H2 plus O2 yields 2H2O, and I put a 2 there. If they gave me 1.0 moles of hydrogen and 3.0 moles of oxygen, that is my clue that this is a limiting reactant problem because both of my knowns are on the reactant side. So there's going to be 2 knowns and both knowns will be on the reactant side. So that's my clue. This is going to be an LR problem. Okay, now limiting reactant problems are pretty easy to work once you've gotten past number 2 and you've recognized that it's a limiting reactant. So to do this, to work one, you're going to pick a product and solve for the product twice. One time for each known. All right. So once I have realized, hey, I've got a limiting reactant problem, to work a limiting reactant problem, I'm going to have to work two problems. So let's look at this one. How many products do I have right here in this particular problem? How many products do I make? I have one. One water, right? I mean, I make one type of product, water. There's two waters, but there's only one product, okay? So for this particular problem, something just made a weird racket in my refrigerator. Did y'all leave somebody alive in there? We're supposed to kill the people before we put them in the fridge. All right. So anyway, so this particular problem, I only have one product, okay? So I'm going to solve for this product right here, water. Now let me ask you, you've worked enough stoichiometry problems. I have moles of my known. What would be the easiest problem to work to solve for the unknown here? I can pick any unit that I want. I can solve for moles or I can solve for grams. What's going to be the easiest thing to do?
Moles.
Moles. See, y'all learned. Try to work smart, not hard, okay? So I'm going to solve for moles on each of these. So I'm going to say 1 mole of H2. I'm going to do my mole to mole ratio. 1 mole of H2 on bottom, 2 moles of H2O on top. That cancels, and I'm going to get 1.0 moles of H2O. So this is my answer. I have to do the exact same thing with the other one. So I have 3 moles of O2. There's 1 mole of O2 to every 2 moles of H2O. So 3 times 2 is 6, divided by 1, 6.0 moles of H2O. So that's step 3. Okay, so step 1, I identify my knowns from the product. Step 2, I identify that this is a limiting reactant because I have 2 knowns and they're both on the reactant side. Step 3, I pick one of the products. Well, in this case, there was only one product. And I solve for that product twice, one for each known. And I'm going to pick the easiest unit. Unless they specify they want to know how many grams or how many moles, you get to choose. And we chose moles because that's easy. So let's look at what step 4 is going to be. Step 4, smallest answer in step number 3 indicates the limiting reactant. All right, so here is your trick question. What's bigger? It's not really a trick question. Here's your bonus question. Which is bigger, 1 or 6? 6 is bigger, right? So 1 is my smallest, right? So my limiting reactant is H2 because that's the reactant. This is the product. So my limiting reactant in this particular problem is H2. So that means that I could make 6 moles of water, but I run out of hydrogen. I have plenty of oxygen, but I don't have enough hydrogen. This would be like me saying, I have plenty of milk to make my brownies. I could make 12 brownie recipes, but I'm going to run out of eggs because the eggs were my limiting reactant. So whatever your smallest answer is, that reactant is your limiting reactant. Okay, so is everybody good? All right. So let's look at step 5. Now, step 5 is a sometimes, okay? This doesn't always work. Look, Claire Beth has got like, half the zoo there. Uh, so step 5 is a sometimes thing, okay? If other problems need to be worked, only use the known limiting reactant for your given. And let me explain what that means, okay? Let's just say that after you've identified your limiting reactant, they want to know how many grams of H2O can be made. Okay? They want to know how many grams of water are going to be produced. Well, I can work this out. That's a simple mole to gram problem. But which known am I going to use? Do I use the hydrogen or do you use the oxygen?
Hydrogen.
Hydrogen. Because if I use oxygen, that's false. That's false pretenses. Because we know that I'm going to run out of hydrogen. So it doesn't work that way. So I would have to make sure that from that point on, any problem that they ask me, I have to use the limiting reactant. So I would say 1 mole of H2, and then that's 2 moles of H2O, 2 moles of H2, and then in 1 mole of H2O, there is 18.02 grams of H2O. So all that cancels out. And then I would run it through my calculator. And I'm going to get, oh, that was stupid. I could have seen it. 18.02 grams of H2O. So that's my answer. Okay. If I worked that problem but used the 3 moles of oxygen, it would be incorrect because we know we can't make that many moles of water. So therefore those grams wouldn't be correct.
Could you have started with your 1 mole of water?
Oh, yeah, and just converted that to grams?
Yeah.
Sure, you could have. Yep. Okay, so these are the steps to working a limiting reactant problem, okay? The steps will help you identify and then to make sure you stay on the right track. When you work these problems, I would put this on the sides. That way you can kind of follow them. Now, limiting reactant problems, there's not a whole lot of them. We don't do them a whole lot in general chemistry. Matter of fact, I'm one of the very few general chemistry teachers that probably make you do limiting reactants. A lot of the other ones skip, but it's part of your curriculum, so I think it's important that you learn it. And to me, it's not that difficult once you get the concept, okay? And normally in class, we would all have brought chocolate bars and marshmallows and graham crackers. We would be making s'mores today. I know it sucks. So if you go to Walmart, get you some s'mores and set you up a limiting reactant problem with your family, and you can teach them about limiting reactants by using s'mores, okay? And it's a great thing because some of y'all wouldn't get enough marshmallows. Some of y'all would get too many graham crackers, things like that. And we would identify the limiting reactants. And so, it's something that's a pretty basic concept, but for some reason, students get really hung up on step number 2, okay? So what I want to do is I want us to look at this first problem. Now, if you've watched the video, you've seen this problem worked already because this is the problem that I work out in the video. But sometimes when I can work them out and talk to you as we do it, it makes things a little bit easier to understand. So we're going to go through this one together. So silicon dioxide is quartz. And it's usually very unreactive, but it does react with hydrogen fluoride pretty readily, okay? And so the very first thing that we need to do is they've given us a reaction. So I want you to take just a second, look at that reaction and tell me, is it balanced? All right, I'm seeing no's, okay? So it is not balanced. It is not a balanced reaction, okay? So I want you to take just a second and write that one out and balance it for me. Okay, so to balance it, I put a 4 in front of hydrogen fluoride and a 2 in front of water, and now it's balanced, okay? So our problem states if 6 moles of hydrogen fluoride is added to 4.5 moles of silicon dioxide, which is the limiting reactant, aka another name for it is limiting reagent. So I'm going to go write my knowns down. So I'm going to write down 6.0 moles above my hydrogen fluoride. And I'm going to come over here and write 4.5 moles of my silicon dioxide. So looking at my steps, step 1, I've identified the knowns. Okay. Now let's just pretend that there wasn't this blazing title, limiting reactant. So we didn't know that this was a limiting reactant worksheet. We had no idea. The next thing that I would notice is I would go, okay, I've got to work this problem. And let's say that they didn't say it was a limiting reactant. And so I've written down my 2 knowns, and that's why it's important to write down your knowns. And I realized, I've got 2 knowns, and they're both on the reactant side. That is my clue that, hey, this is going to be a limiting reactant problem. So please beware that when you take your test on Friday or when you're working problems, you may not have this, flashing sign that says this is a limiting reactant, this is a limiting reactant, this is a limiting reactant. It may be something so subtle as how many moles of water can be made. And it doesn't say anything about it being a limiting reactant. But that's okay because a limiting reactant has 2 knowns, both on the reactant side. Okay, so let's look at so now we know it's limiting reactant. So step 3, we're going to pick a product. Okay, so I'm going to look at my products and I'm going to go with silicon tetrafluoride because it's a 1. All right, and so I don't have to worry about this 2. So this one's going to be mine. And I'm starting with moles and I don't want to work hard. So I'm going to look for how many moles of silicon tetrafluoride. Now, could you have picked water? Absolutely. Okay, you could have picked water. That would have been fine. But I'm going to pick this one because it has a 1. All right, so I'm going to do my problem. I have 4.5 moles of silicon dioxide, and that's 1 mole of silicon dioxide on bottom, 1 mole of silicon tetrafluoride on top, and that's, of course, going to give me 4.5 moles of silicon tetrafluoride. So there's my answer for the first one. Am I done? Can I quit? No. What do I have to do now? By your fingers, I know that means I have to work it with the other one. That's right. So I'm going to go with 6.0 moles of hydrogen fluoride. And I have 4 moles of hydrogen fluoride based on my mole to mole ratio and 1 mole of silicon tetrafluoride. And I'm going to run those through my calculator and I'm going to get 1.5 moles of silicon tetrafluoride. Okay, Now, I'm going to have a lot of students who work it to that point, and they're going to be like, I feel good about that one. Next problem. But we have not answered the problem. The problem wants to know, what is the limiting reactant, which means I have to identify my limiting reactant, not limiting product, limiting reactant. So which one of these is the smallest? This one, 1.5 moles of silicon tetrafluoride. So that means which reactant is the limiting reactant? Is silicon tetrafluoride the limiting reactant? No, it's a product. What's my limiting reactant? Hydrogen fluoride.
Hydrogen fluoride.
That's right.
I didn't know how to say it exactly, so I was like,
So right over here, I'm going to put HF is the LR. And if you had seen that on your paper 48 hours ago, you would have been like, what weird language is that? But now you know hydrogen fluoride is the limiting reactant. Now, for this problem, we're done. Yay! They didn't want anything else. They didn't want us to find grams. They didn't want us to find anything else. Had they wanted us to work another problem, we would have had to make sure that we use this as our known from here on out. I would probably go up and, just as a rule of thumb, X this one out. So that way I would know that I don't need to use it to answer any more problems. Okay? Because we need to make sure we use this as our known from that point on. All right, are we good? So let's go on to the next one. The black oxide, Fe3O4, occurs in nature as the mineral magnetite. This substance can also be made in the laboratory by the reaction of red hot iron and steam. Okay, so they've given us a reaction. Take a second, look at that reaction, see if it's balanced. If it's not, balance it. Okay, so I say 3Fe plus 4H2O yields Fe3O4 plus 4H2. So that's how I'm going to balance it. Okay, so let's look at the three different parts. Part A says when 36.0 grams of water, so I'm going to go immediately above my water, and I'm going to write 36.0 grams of water is mixed with 67.0 grams of iron. So I'm going to go put this over here. They want to know which is the limiting reactant. Okay, so once again, they've spelled it out for us. They've told us our knowns, and then instead of letting us guess what we're going to be doing, they just say, hey, find the limiting reactant. So we can do that. So I picked Fe3O4, and the reason why is because it has a 1 coefficient, so that makes my problems a little easier to work. So this is going to be my reactant right here, or my unknown. So I'm going to put a little question mark over it. Now, normally, I would say grams to moles because that's easier. But do y'all notice that this is a 3-part problem? Whenever I see a 3-part problem, I go ahead and look at what they're looking for later on, because that means I may only have to work a problem once. And y'all see right here in B, it says mass in grams. And right here in C, it says mass in grams. So just to save me some time, I'm just going to look for grams from the get-go, because then I'm just going to be having to work 2 problems, when I could have done it the first time. So I'm going to look for grams. Now, you could have chosen to do moles, and that's fine. And if they didn't ask for anything else, I would have stopped at moles, because we want to work smart, not hard, okay? All right, so for part A, they want me to find the limiting reactant. So I'm going to do just like I did before. I'm going to start with my 67.0 grams of Fe. I'm going to find my molar mass, 55.85 grams of Fe and 1 mole of Fe. And then in 1 mole, 3 moles of Fe, I have 1 mole Fe3O4. And then I'm going to do molar mass again, 1 mole Fe3O4. And that is 231.55 grams of Fe3O4. Cancel out all my givens. All my like value units. So 67 times 1 times 1 times 231.55 divided by 55.85 divided by 3, and I get 92.6 grams of Fe3O4. Am I done? No. I got to do the same thing for my other one, right? Which was water. So I'm going to say 36.0 grams of water. And in 1 mole of water, there's 18.02 grams of water. And then I'm going to do my mole to mole ratio. 4 moles of water on bottom, 1 mole Fe3O4 on top. 1 mole of Fe3O4 on bottom. 231.55 grams of Fe3O4. Cancel out all my like units. Run it through my calculator. And
Miss Fort Mary,
yeah.
how'd you get the 18.02 grams of H2O?
That's its molar mass. 2 hydrogens and 1 oxygen.
Oh, okay. Thank you.
No problem. That's a good one just to memorize. Okay. So I'm going to go ahead and tell you that when working these problems, you have options. And when I grade limiting reactants, I have all the options worked out too. You could have chosen to just look for moles. You could have chosen hydrogen and looked for grams or moles. So any of those would have been fine to have done. There's like 4 different options that you could have picked. Either way that you work it, or any possible way that you work it, as long as you've worked it correctly and you set it up correctly, you still should get the same answer. So let me ask you, which reactant is my limiting reactant?
Iron.
Very good. Iron would be my limiting reactant because it has the smallest answer. Okay. So let's look at B. For B, they want to know what mass in grams of black iron oxide is produced. So would I make 92.6 grams or would I make 116 grams?
92.6,
Why?
because it's the limiting factor.
That's right. That's the only thing that I could make. It's like the brownie mixes. I can only make 6. So this is how many grams. So because I went ahead and worked it out the first time, my next answer would just be 92.6 grams of Fe3O4. Now part C, you'll notice it says omit, and that's because we don't worry about finding the remaining of excess in here. You know, one day if you're really bored when we get back to school and you want to come in at break, we'll do some. You'll enjoy it. Oh, Claire Beth White's got her critter here too. So anyway, so we can work some together later on, but you don't have to know it for this test, okay? So I do want to point out that on the test there will be 2 limiting reactant problems. One's going to be pretty obviously stated, and the other one's going to be a little bit more subtle. So therefore, you're going to have to figure out if it's a limiting reactant, and then you're going to have to work out some extra problems to kind of go along with it. Kind of like this. It's going to be a more than one part, okay? So does anyone have any questions about limiting reactant problems? Awesome. So let me stop the recording then.